Hi everyone, I am Kazir Riazul Hassan. Very pleased to meet all of you. Hope everybody is having a great time at Kolkata. And apologies from our side that we couldn't be present in the conference in person and have to present it online. Anyways, so we move on to the topic. My co-author and supervisor Muhammad Abdullah Adnan and I engaged in over this research lifespan. We worked under the affiliates of Bangladesh University of Engineering and Technology, and our goal was to develop a systematic framework for word-level sign language recognition, primarily targeting Bangla, and then moving on to other sign languages for benchmarking results. From that goal, we proposed EMPATH, a media pipe, transformers, and ensembling-based model. This is the component paper discussing on implementation and reproducibility notes on EMPATH, enhancing word-level sign language recognition. This is the basic overview on how we will like to proceed with our presentation. The presentation will roughly contain all these points in greater detail. So moving on. What exactly is sign language then, and how it differs from gesture recognition problems? Sign language is an established way of communication of the deaf and hard of hearing people, having specific letters, words assigned to each sign, and ultimately coming to unanimity. Meaning in our country, Bangladesh, all the deaf and hard of hearing people use the same sign language. And for the example of our neighboring country, India, everybody there will use Indian Sign Language. In the image, we can see two image sequences taken from videos, which represent the given signs mentioned in the caption. Though there are some lexical similarities between closely related languages, there are clear and distinct differences between two different countries' sign languages as well, like the natural languages alphabets of, suppose, English and Hindi. Okay, so now the problem can be easily identified. We people who can speak in natural language normally don't know sign languages, and thus this creates a heavy barrier of inclusivity. We need to understand what they are trying to say by using those signs, and this includes all of us. Research for detecting and recognizing sign language through technology has been continuing for a while. It can be divided into three categories. The first one is sign language detection from image modality, like in the image right here of ASL, data level ASL. This is currently a saturated task, meaning almost no room for improvement. The second and the third one are a bit more complex. Word level recognition from video modality is what we are targeting in this research. So why do we exactly pick up? As we aim to target Bangla Sign Language first, but there have been a few works, not many actually, like the recent works we can see. This one right here, Sign BD Word, where the authors created a new Bangla word level dataset of 200 levels. And then we can see another work. This dataset was mainly adopted from Include, an Indian dataset, by doing mapping with Bangla Sign Language Dictionary. And then we can look into a few very established works from other sign languages. The first one here is WLASL, which proposes a huge dataset of 2000 sign words, and then the include dataset itself right here on the right side, an Indian dataset, sign language dataset of 250 words. So this is also a very interesting word, and up until now what we have discussed is now more focused on dataset creations, while Bangla Sign Language also lacks in that too as well. Like the previous two mentioned works are almost the only works on the dataset. So the research gap, it's pretty clear. Now, what we are trying to say is that none of these works have focused on proposing a generalized, powerful model with advanced SOTA techniques, rather focused on dataset creations, which is obviously a fundamental thing to do when we start working with sign language. So now from there, we pick up and continue advancing research techniques. We already got a few datasets from the sources mentioned earlier, and ultimately we focus on building a comprehensive framework which should work not only in Bangla Sign Language, but also should be able to generalize well. This is the research gap we identified and the motivation of developing EMPATH. So all these talks are not directly related to implementation and reproducibility, but knowing why we wanted to do it should inspire us to go into the details of how we did it. So the contributions, we developed EMPATH framework using media pipe holistic attention-based transformers and ensembling techniques. We also developed a novel interpolation model to address missing hand key points. This is an interesting idea, and we'll come back to it soon. We also custom built our transformer from scratch and tried to make it as lightweight as possible. And then we set new benchmarks, not only on the Bangla Sign Language datasets, but also test its power on other sign languages as well. So finally, we move on to the implementation part. We can see our proposed model here. We start off taking the raw RGB videos and extract key points from those using MediaPipe Holistic. We also fix the key points at that step as well, the missing key points. And then we save the data of key points coordinates into Parquet files. Our main transformer model is fed with the frame data from each video. You can think of the video frames to be tokens, as that's how we normally recognize transformer models input. The key point values can be thought of as features of that frame, aka token, and the multi-threaded attention process puts weight on how each frame is related to each one another. Ultimately, we go through the whole process of embedding, positional encoding, FNN, all the common processes of a transformer. We also use probabilistic augmentation techniques and train a total of 4 transformer models. We do an ensembling of 4 models based on majority voting, and then we get the final prediction from the model. So this is the workflow. You can see total of 4 steps right here: pre-processing, key points extraction, training, and inference. The outcomes from each step is given on the right. Like first we get the respective CSVs, then the Parquet files. After training, we get the model, and then we perform the prediction metrics based on the model inference. So before giving our transformer model any input and actually starting the training process, we can think of everything before that as pre-processing steps, not differentiating key points extraction as a different step here. Our setup of MediaPipe Holistic is given here. We try to balance inference speed and accuracy. Normally, MediaPipe Holistic can support complexity level of 2, but we chose 1 for this reason. Inference here means that the media pipe outcome results, don't get confused with the overall prediction results here. So our choice of putting all the extracted key point coordinates into Parquet files, individual Parquet files, is simply because it's fast and compact. Okay, so we have talked a whole lot about key points extraction. So what exactly is this and how does it benefit us? You can think of it as our joints or points in our body, which models like YOLO, OpenPose, MediaPipe right here can directly detect, and it helps us to capture pure movements and positions of hands, pose, face within the frames or videos, and it eliminates that backgrounds and other aspects from behind. So the backgrounds and other aspects do not get any weight when it goes through the model. So this is a savior, because you can see that for the example of sign language, and image is given here, you can see that the man is raising the hand. We can already see this key point image in the middle, and from this key point image we can also say that the man has raised his hand. We do not need the whole image, the whole body shape, to understand what this man is doing, and that's the significance of how we can utilize key points extraction in sign language. Okay, so now we highlight an interesting problem of key points extraction in context of MediaPipe as we are using it. It struggles to capture rapid and very fast movements in videos, sometimes misses to detect key points, which is necessary input for our training model. Like here, we can see the image on the left. The problems here are actually 2. It failed to detect one hand right here, no key points here. And then again, on the other hand, the wrist and hand are not aligned for the case where it did detect the hand. So you can see that the wrist has gone here, but the hand key point is right here. And on the right image, both the hands were not detected from the MediaPipe. So it's because probably the video speed, like the signer was performing the sign a bit fast, so it couldn't really detect all these key points. So one way to think of it as that these frames, we can simply drop them out because these do not have those hand key point values. And another approach we can go is that we can mark those key point values as 0, which is also not a very good solution, as key points are clearly in arbitrary positions on the frame. Okay, so to solve this problem, we propose our interpolation model. It solves both the problems of missing hand key points and hand wrist misalignment. If we do not go explaining any complex formula, the base idea is we use the notion that we can calculate the positions of each key point for a frame if we know where the key points were in the previous frame and the next frame. So the key points will definitely be somewhere in the middle of those two. This is how mathematically we do the calculations. And this actually works really well. As you can see in the image example, the left one was taken from the previous slide example where both hands were undetected. And here we can see that after the interpolation model result, both hands are pretty much very accurately detected, and wrist and hand are also properly aligned. So just a small review on the batch size right here on the algorithm perspective. This batch size right here, we declare it as a size of how many frames media byte process before we go back and fix the frames with missing key points. A notion taken from garbage collector ideas of operating system. If we make the batch size way too big, we will need to store a lot more frames information in a list, and that may exhaust memory. And if the batch size is too small, the inference time will increase as it will continuously go back and try to fix previous missing frames. So selecting optimal batch size is also a decision to make. We will come back to that later. Okay, now to our training transformer model. The hyperparameter set here are all experimented, like the epoch size, for example, we set it to 300. And here is just an example of the experiments we carried out. We can see that almost on 280 achieved highest training accuracy, which may be a desirable approach, but yes, we had to ensure that we also avoided overfitting. The other hyperparameters are pretty much self-explanatory, so you can play around with it. And one thing to note is that we used TF Lite to make the transformer lightweight, and that needed some coding from scratch. Here we can see the overall transformer structure. It's a bit hard to see and explain each step here, but no need to get overwhelmed. The operations are native to multi-headed transformer design. We'll leave it to the audience to go into the bits and pieces of this architecture, proposed originally in the legendary work Attention is All You Need. Okay, so the code base is publicly available and anyone can use it. We have tried to document each and everything as much as possible, whether someone aims to implement it from scratch or simply check if our works actually work. We have provided all the details along with the pre-trained models and also the Parquet files that were used for training and testing. The codes are commented properly so that each step is comprehensive enough as well. We recommend anyone who feels interested in the work to visit the GitHub link. There are a lot more details to be found there. Okay, so we have discussed about theories and implementation details thus far. Now we will see some experimental results on how we decided to develop EMPATH the way it is. We start off by recalling our missing key points problem from MediaPipe. This is actually a pretty significant problem, and we can see the severeness of it into longer videos. That's why we chose two sentence level datasets here, Phoenix 14T and How to Sign, obviously because in sentence level the videos will be larger of size. If we see the results as Phoenix T for Phoenix 14T is low resolution videos, we can see a data loss of almost 1 of 3, so 30%, which is huge. And even on high quality data set like How to Sign, there were like 10%, almost 10% of data loss. So it is quite clear that our approach to fix missing key points is actually well motivated. So to validate our interpolation model, we first start off with raw experiments. We needed to figure out if that it has noticeable improvements, like the interpretation model has noticeable improvements before incorporating it into EMPATH. For that, we take a pre-trained transfer model, which is trained on Google isolated sign language dataset, which is 250 American Sign Language words. We then test the model from instances generated in-house following original ASL and examine each instance separately. In the right, we can see the examples of that creating test set. The good part about creating our own instances was that we could vary the real life scenarios like lightning, brightness, some parts covered, etc., and how our interpolation model makes a difference we can actually see. Okay, so the results, we tested a total of 52 different word instances, and the results were actually assuring. Predictions with the interpolation model showed a 7.692 increase in accuracy, and prediction confidence boost was almost 6.297%, than just base MediaPipe holistic. While there are instances like this zebra ground truth, MediaPipe only prediction and MediaPipe plus our algorithmic interpolation model prediction both are wrong. It couldn't fix it, but improvements were noticeable as seen in both tables results. Another reassuring fact was that it rarely deviated from the original MediaPipe results of correct answers, meaning what I'm trying to say is that MediaPipe made a correct prediction, and our MediaPipe plus algorithm approach is worsening the performance of it. It did not happen frequently, but rather rarely. So we can see a bit of visualizations here. On the top right, we can see the hand is missing from the coordinate frame, and on the left, how we regenerated it. On the bottom, for the same test video of ground truth, our simple approach of recovering data yielded the correct answer, and raw MediaPipe made a false prediction, and the separation from other levels was also away from the correct one as well. Okay, now we are most likely to believe that the approach is working well, but we are adding a new layer on the process. How does it change other aspects like inference time and memory usage? And ultimately, are the trades-off worth it? To calculate inference time and memory management, we used Python's time module and Python's Guppy module. If we recall the concept of batch size, then that was the variable we needed to fix actually. So we saw that batch size of 20 frames, or more like the FPS of that video. Like if a video is 25 frames per second, setting that as a batch size, meaning every 1 second we go back and fix the missing key points, is actually a pretty good approach from our experiences and experimentations. We could see that. The memory usage does get a bit higher as we increase the batch size, which is normal because we need to store more data in the list. But then again, most of the devices are equipped with gigabytes of RAM nowadays, so it's not a big fact. And about inference time, that is barely noticeable as well, which is only 1.83% increase in inference time. So we can safely conclude that we can afford these slight trade-offs to get the performance gains. Now we'll briefly talk about another implementation detail within our training, the two augmentation techniques we used. Frame drop augmentation, as we can figure out from the name itself, probabilistically drops frames in between from the video, and time scale augmentation plays around specific video's parts speed, making that specific part slower or faster. Again, that is done probabilistically. So we needed to make sure that we do not greatly vary those. And here we can see that the accuracy and basically the combination of these two augmentation techniques varies for each dataset. Like for which dataset it will perform better, that is also something we need to figure out by experimentation, because we can see that there are variances of these two results where we get the most accuracy. Okay, so finally, we do agree that our work has some limitations, like there is no dictionary level dataset with which we can recognize all the words. The results will be affected as we increase our dataset size. So we'll probably have to settle with a structure like ChatGPT, where we need to request the core model via APIs, because as we increase the word count, the model itself will get larger. That also raises the question of total time required. And then again, another struggle we face is running media pipe holistic on GPU. The overall documentation was not clear enough. And at the end, we had to process all the videos on CPU, which was a time-consuming task. In future works, we look forward to acknowledging these limitations. So these are our acknowledgements. That pretty much wraps things up. Thank you so much for attending. Before we move on to the Q&A session, we would like to invite you to attend our oral presentation tomorrow at session 1C at Hall 6 from 11 a.m., where we analyze this work in more vivid detail. Thank you again.